Hello friends, I am Professor Rajendra Koranne from my YouTube channel Teach Easy. In previous two videos, I have explained you the step-by-step procedure of design one-way simply supported slab and two-way simply supported slab. Now in this video lecture, I will explain you the step-by-step procedure of designing a one-way cantilever slab. Design a 2-meter wide cantilever chhajja of span 1.5 meter. It has to carry a live load of 1.5 kilonewton per meter square and floor finish of 0.5 kilonewton per meter square. The supporting lintel is 230 mm by 300 mm. Use M20 concrete and Fe415 steel. Sketch the cross section of the chhajja showing reinforcement details. Now this is the problem asked in MSBT exam for 6 marks. So with the help of this problem, I will explain you all the steps involved in the design of cantilever slab. Before we start with the design, let me tell you one important thing regarding the cantilever. As all of you know that cantilever is fixed at one end and free at other. Whenever it carries downward point loads, it bends in a hogging fashion, inducing tension at the top and compression at the bottom. Therefore, the main reinforcement which is to be provided for cantilever should be provided at top. This is one of the important points. And now let us see how to solve this problem step by step. Let us first write down the given data. Now in this given data, we are given the span, that is 1.5 meter, then live load is given, intensity of live load, how much it is, 1.5 kilonewton per meter square, then floor finish is also given. Now as it is a chhajja, floor finish and live load is less. Floor finish is 0.5 kilonewton per meter square. And as usual, grade of concrete and grade of steel is given, that is M20, that is FCK will be 20 Newton per mm square, and Fe415. These are the materials which are to be used. And the dimensions of the lintel beam is also given. Supporting beam, it is 230 mm wide and 300 mm deep. Okay, so these are the things which are given in the problem. What is required? You have to design the slab, means you have to find out the depth of the slab, as well as you have to find out the reinforcement required in this. Okay, so let us start for the solution. Before we start for the first step, let us first assume the percentage reinforcement from which we can assume modification factor. So assume percentage PT is equal to 0.35, and as the grade of concrete is Fe415, definitely value of MF for the assumed percentage of steel will be 1.4. Okay. Now let us start with step number 1. What is step number 1? To find out the trial depth. Okay. The trial depth which is denoted by letter small d is equal to L upon, as it is cantilever, the basic L by D ratio is 7. So it is 7 times modification factor. This is important to note that for cantilever, basic L by D ratio is 7. Okay. So I will put L is equal to 1500 upon 7 multiplied by modification factor 1.4, and this comes out to be 153.06 mm. Say we will round it up, 155 mm. Okay. So let us round it to 155 mm. So this is effective depth. Now definitely, assuming effective cover of 20 mm, overall depth what will be overall depth? Capital D will be equal to 155 plus 20, that is 175 mm. This is overall depth. So first step is over. Now let us go for step number 2. That is load calculation. Load calculations. Now for this load calculations, definitely we consider 1 meter wide strip. Okay. So for 1 meter wide strip, now we know that design load is always working load multiplied by partial factor of safety, that is 1.5. So this formula I have already explained in the design of one-way simply supported slab. So 1.5 into bracket 25 times capital D, where capital D is overall depth of the slab in mm, plus live load, that is the intensity of live load in kilonewton per meter square, plus floor finish, that is intensity of floor finish in kilonewton per meter square. Okay, this will be definitely in kilonewton per meter. So let us substitute 1.5 multiplied by into bracket 25 into D. D is 175 mm. So in meter it will be 0.175 plus live load into 1. So live load intensity is given as 1.5 plus floor finish is given as 0.5. So if you equate this, it comes out to be 9.56 kilonewton per meter. Okay. Now, before we go for the next step, that is design moment, we will have to first calculate the effective span. Okay. Now, as per clause number 22.2 C on page number 35 of definitely IS 456 2000 the effective length of the cantilever is to be taken as the projected length, that is L, plus D by 2, where D is the effective depth. Now here the cantilever is projecting 1.5 meter, so it will be 1500 plus D is 155 by 2, which comes out to be 1575 mm. That is 1.58 meter. So this is one of the important things as far as the cantilevers are concerned. For cantilevers, effective span is definitely the length of the cantilever projecting out from the lintel plus the half of the effective depth of that cantilever slab. Okay. Step number 3, design moment. All of us know that the design moment for the cantilever MD, design moment MD is equal to WD into LE square divided by 2. So let us calculate MD. So that is design load is 9.56 into LE is 1.58 square divided by 2, which comes out to be 11.93 kilonewton meter. Okay, so this is the design moment. Now let us go for the next step. Step number 4. What is step number 4? Check for D for BM. Check for effective depth D for BM, means whether this depth is sufficient to resist BM or not. Now while checking for D for BM, we have to equate MD with MU limb. Okay, so now we know that for Fe415, because we have to use Fe415, what is MU limb? MU limb is equal to 0.138 FCK B into D square. Of course, this is in Newton mm. Okay, so equating MD with MU limb, let us see what we get. MD is 11.93 kilonewton meter, so multiplied by 10 raised to 6, because we have to convert it in Newton mm, is equal to 0.138 FCK is 20, B is width, we have assumed 1000 1 meter into D square. So both sides are in Newton mm. Okay, therefore you get the value of D as, solve it for D, 65.75 mm, which is definitely less than D provided. D provided is 155. Therefore safe. So this D which we have provided is sufficient to resist the bending moment. Now let us go for the next step. Step number 5, that is reinforcement. Reinforcement. In reinforcement, there are two parts, A and B. A is for main reinforcement, and B is for distribution. So let us go for part A, that is main reinforcement. Now, one important point you have to keep in mind, that as it is cantilever, the main reinforcement is to be provided at top, because the tension will be induced at the top. Okay. Now, let us use the usual formula of 0.5 FCK upon Fy. Okay. So here, instead of writing the formula, I will save some time by substituting the values directly. So ASTM, that is area of steel reinforcement main, 0.5 into FCK, that is 20, upon Fy, that is 415, into bracket 1 minus under root of 4.6 MD. What is MD? Design moment 11.93. Important to convert it in Newton MA into 10 raised to 6. If you forget to multiply by 10 raised to 6, whole calculations will go wrong. Divided by FCK, that is 20, B, that is 1000, D square, small d square, that is 155 square, into B into D, again B is 1000 and D is 155. So this is our usual very important cinemascopic formula. If you calculate it, you will get the answer as 219.75 mm square. Now, let us check for AST minimum. Okay. What is AST minimum? That we will check now. AST minimum is equal to, always as we are using Fe415, it is 0.12% of BD so this will be 0.12% means 1.2 times D, overall depth 175, which comes out to be 210 mm square. Now here it is very clear that AST main is greater than AST minimum, therefore OK. Do you understand this? This is OK. Now, after finding out this area of reinforcement, we have to find out spacing. So how do we find out spacing? Providing use rather 8 tar bars. Okay, spacing is equal to How do we calculate spacing? Spacing is equal to, yes, 1000 into small ASTM upon capital ASTM. Okay, so put the values. Small ASTM is cross-sectional area of one 8 mm tar bar, so which comes out to be 50.27 divided by AST main we have calculated 219.75. The spacing is equal to 225 mm. This is main steel. So main steel, for main steel, definitely the check for maximum spacing. So what is maximum spacing? Maximum spacing is equal to main steel. So it is 3D or 300 mm. Okay, so here 3D is equal to 3 into 155 is equal to 465 and second is 300 mm. Whichever is less, so this is lesser, and you can very easily see that this spacing is not greater than this maximum spacing, therefore it is okay. Do you follow this? Check for maximum spacing. Okay, now the next step, that is part B, distribution reinforcement. The main reinforcement we have calculated, distribution reinforcement. Okay, use 6-5 bars, 6-5 bars means mild steel bars. Therefore, for mild steel, area of distribution steel is always 0.15% of gross cross-sectional area of concrete, that is BD, which comes out to be 0.15 upon 100 into 1000, that is 1.5 into 175 overall depth, which comes out to be 262.5 mm square. Okay, now let us find out the spacing. How do we calculate the spacing? Spacing is equal to 1000 into small AST, that is area of 1 bar of 6 mm diameter, upon ASTD. So 1000 into area of 1 bar of 6 mm is 28.27, upon 262.5. Which comes out to be 107.70 mm. Okay, so we can say 105 mm. Now you can apply the check for maximum spacing. Spacing is equal to 105 mm. Now again, what are the criteria for maximum spacing? The spacing of distribution steel shall not exceed, yes, maximum spacing 1, 5D, and second 450 mm. 5D will be definitely 5 into 155 will be much more. So you can very easily see that minimum of these two will be this, and we know that this particular spacing 105 is not greater than maximum spacing, and therefore this is okay. Okay, so this is reinforcement. Now let us go for step number 6. This is important step, that is check for percentage PT. Check for percentage PT. Because in the first step we have assumed percentage PT as 0.35. So if this percentage PT is less than that, that is okay. Otherwise we will have to revise the design. Okay. So for this purpose we will have to find out actual AST provided. So AST provided how to calculate AST provided is 1000 main steel into area of 1 bar of 8 mm diameter, that is 50.27, upon the spacing which we have provided, that is 225, which comes out to be 223.42 mm square, as against 219 point something it is, 75. 219.75, from that we get the spacing as 228, and we are providing 225, so it will slightly increase. Now this is actual AST provided. Once you know the actual AST provided, we can find out percentage PT is equal to 100 into AST provided upon BD. So put down 100 into 223.42 divided by B is definitely 1000 and D is 155, which comes out to be 0.15. Okay, which is not greater than percentage PT assumed. Therefore, it is okay. This is one of the important steps in this, because we have assumed percentage PT. So if you have assumed it, you have to check it whether it is proper or not. The assumption is proper or not. Our assumption is definitely correct. Okay, check. For development length. Now let us apply the check for development length. Okay, now for concrete M20, and plain bars in tension, we know that design bond stress tau BD equals to 1.2 Newton per mm square. This is as per IS 456/2000. Okay. Now here Fe 415 is used. Okay. So therefore, for Fe 415 bars in tension, tau BD will be, we have to increase it by 60%. So 1.2 increase it by 60% means multiplied by 1.6, which comes out to be 1.92 Newton per mm square, designed bond strength. Now The development length required, LD required. How do we calculate LD required? It is equal to 0.87 Fy upon 4 times tau BD into phi. So if you put the values, 0.87 into Fy is 415 into phi is 8 divided by 4 into 1.92, which comes out to be 376 mm. Now this much LD is to be provided. Okay, so LD provided, I will explain it from the drawing. So LD provided is equal to 230 minus 25 plus 125 minus 25 plus 230 minus 50. So definitely this will be, so how much it is? 230, 460. 460 minus 100, that is 360, and plus 125, that is 485. I will explain this when I will show you the cross section. Okay, so as this LD provided is greater than LD required, the cantilever slab is safe for bond. It is definitely safe for bond. So this is important. This was the last step. Now I will write the summary and then figure. That's all. Summary. Now what is the summary? First one, effective depth equals to 155 mm. Now this effective depth will be provided at the fixed end only, because as you approach towards the free end, bending moment reduces, so you can reduce it. So I will explain it when we will draw the figure. Capital D equal to 175 mm. Main bars what is main reinforcement? 8 torr at 2 to 5 mm center to center. Very important to note, that is to be provided at top because it is cantilever. And the third one is distribution steel. What is the distribution reinforcement provided? Yes, 6.5 at 105 mm center to center. So this is the complete solution of the problem. Only one point is remaining, that is the sketch. So this figure shows the cross section of a cantilever carrying reinforcement details. So you can see here, this is the lintel, 230 mm wide, 300 mm thick, and this is the projected part of the chajja, that is 1.5 meter. Okay, now I have told you that at fixed end bending moment is maximum. As you approach towards free end, bending moment reduces, so can you can reduce the depth. So at fixed end the overall depth is 175 and at free end it is kept as 100. Okay, and this is the supporting lintel. Now you can see here that this red bars, this red line provided at the top is the main reinforcement, that is 8 tor at 225 center to center main reinforcement. These blue dots are 6.5 at 105 center to center. These are distribution reinforcement, and you can see that what is LD provided. I will show you. See, look here. So this is the bar provided at the top, and from here to here, here, this is the LD provided. So if you see it, it was 230 minus 15 or 25, that is the cover. Then this distance is 300 minus 175, that is 125. So if you see it, so it is 230 minus 25 plus 125 minus 25 plus again 230 minus 25 and 25, 50, and you can take it down. So in this manner you can provide the development length which is required. So this is the cross section. Mind well, as it is chajja, it is kept plain at the bottom and sloping at the top so that the water can run out. If it is the slab for the balcony, it may be reverse. Okay, so these things are known as chairs. Chairs are provided which are made up of the wastage steel bars. They are provided so as to avoid the bars at top coming at the bottom. When the workers will walk over it, it may happen that this bar comes down and the purpose will not be served because the main steel must be at the top. Okay, so this is how we can design a cantilever slab. Okay, so this is all step-by-step procedure. So thank you very much. If you like this video, share it to your friends. Then subscribe for my channel and hit the bell icon for all so that you will get all the new videos uploaded by me. Thank you.